Our parent chain is et because it contains 2 carbon, and the functional group there is COH. Then we have ethanoic acid first. So at carbon number 2, you notice there is OH there, and the same carbon number 2 there is phenyl group, which gives us 2,2-diphenyl and then 2-hydroxy. In alphabetical order, there should be hydroxy before phenyl. Therefore, the name is 2-hydroxyl 2,2-diphenyl ethanoic acid, commonly called benzylic acid. In this tutorial, IUPAC system of naming aromatic compounds, one should know that R stands for alkyl group, C6H6 is the molecular formula of benzene, C6H5 is an aryl group commonly called phenyl, and the name of any organic compound is derived or divided into prefix, root, and suffix, just like you have your surname, first name, and last name. And in naming, one should name the root first, followed by the suffix, and finally the prefix. Not every organic compound has a prefix, but all must have a root and a suffix. Prefix is gotten from the substituent groups attached to the parent chain. Root is determined by the number of carbon atoms in the parent chain, or the longest continuous carbon chain. Suffix is determined by the principal functional group attached to the parent chain. The possible roots that we can have, can take it like a little song: met et prop, bunt pent hex, hebt oct non, deck on deck. That is from C1 to C11. Met et prop, bunt pent hex, hebt oct non, deck on deck. We will give you the way to name from carbon atoms that have up to 50, 60, even 100. Like 100, we call it hect. When it's up to 100 carbons in the parent chain, we call it hect. Happy watching, and remember to drop your comment in the comment box and ask your questions. Thank you. Welcome to second chemistry tutorial. Topic: naming of aromatic compounds 1. First, let's take a look at what aromatic compounds are. They are organic compounds that contain a benzene ring in its molecules or that has chemical properties similar to benzene. In view of this, aromatic compounds are also called benzenoid compounds. The word aromatic was derived from the Greek word aroma, which means fragrance. This is because aromatic compounds were discovered earlier before they are even studied, and the early members that were discovered all had a pleasant smell, and hence they were given the name aromatic arbitrarily. Example: the balsam, the resin oil, and the aromatic oils. All of them had pleasant smell, though not all of them smells nice for now, but it is obvious that aromatic compounds are benzene derivatives. So let's take a look at benzene. Benzene is the archetypal compound of aromatic compounds. This is because every other aromatic compound is derived from benzene. Benzene can also be called phen. It was first isolated by Faraday from the pyrolysis of whale oil. Then in 1845, Hoffman also discovered benzene in coal. We take a look at structures of benzene. There are many attempts to describe the structure of benzene, but we'll consider only two: the Kekule structure and Sir James Dewar structure. After the discovery of benzene in 1825, its structure remained a mystery to scientists until in 1865, when Frederick August Kekule suggested or proposed a structure for benzene as a hexagonal ring of carbon atoms linked by alternating double and single bonds. This structure contributed to the recent-day resonance structure of benzene, or the resonance hybrid structure of benzene. Later, Sir James Dewar proposed a structure of benzene as a hexagonal ring of 6 carbon atoms with 2 opposite atoms joined by a long single bond across the ring, and with 2 double bonds on each side of the hexagon. These two structures, the Kekule structure and the Sir James Dewar structure, contributed in the resonance hybrid structure of benzene. The representation of structure of a molecule by 2 or more conventional formula is just what we call resonance, and it is applied in stereochemistry. In 1945, the concept of resonance was used to explain the structure of benzene. The resonance structure of benzene is just a hexagon with a ring in it, indicating that the double bond resonates, or that the double bond shifts with time, which means the pi orbitals are delocalized. In numbering of the carbon atoms in the benzene ring, that is, which among the 6 carbons will be number 1. No rule says number from left to right or right to left, or number anti-clockwise or clockwise direction. Rather, the rule is based on the position of the principal functional group. The carbon that bears the principal functional group should be taking the number 1, which means if the OH is attached here, here becomes our number 1. If it is here, here becomes our number 1. Then
In the case of other substituent group that is not principal functional group, you number from the direction that gives them the lowest possible number in relation to the position of the principal functional group. Take this one for example. OH is the principal functional group. Remember, OH attached to benzene ring, we just call it phenol. But we have another substituent group there, which is chlorine. So let's see two possible numbering. Internally, somebody numbered 1, 2, 3, 4, 5, and 6. That means you get chlorine at carbon number 6. Then when you number in this direction 1, 2, 3, 4, 5, you get chlorine at carbon number 2 in relative to the position of OH. Therefore, the correct one should be 2, this one that gave chlorine number 2. And hence, the name of this compound is 2-chlorobenzenol and not 6-chlorobenzenol. Rather, it should be 2 because this OH here, even when the OH is here, it will still be 2 because all the possible numbering that will give you lower possible number should be 2. Now, take a look at this example again. This one shows the same compound with wrong and correct numbering. This is correct, giving you 1, 3. But this person numbered in direction that gave the 2-chlorine 1, 5. Take it that 1, 5 is higher than 1, 3. So you take the lower possible number. 1, 1, 2, 3. Rather, 1, 2, 3, 4, 5, 6. You have it at 1 and 5. But here you have the 2 chlorine atoms at 1 and 3. Therefore, 1, 3 dichlorobenzene and not 1, 5 dichlorobenzene. Take it that 15 is bigger than 13. See another example here. These are two compounds with wrong numbering and correct numbering. In this situation, you have somebody numbered like this: 1, 2, 3, 4, 5, 6. This is wrong because it is not the lowest possible direction. If you follow here 1, 2, 3, 4, 5, 6, you get 1, 2, 3. That should be the numbers that bears the OH. Therefore, this numbering gave this name 1, 2, 3 trihydroxybenzene, while this one gave the name 1, 5, 6. Even if you follow here 1, 2, 3, you still get 1, 2, 3 trihydroxybenzene. This is the correct numbering. This compound is commonly used to absorb oxygen when in alkaline medium. If you take a look at the one that is here, the OH are the para positions. When we teach you how to name disubstituted compounds of benzene, you know what I mean by para positions. We have auto position, meta, and para. Now, in whichever direction you have 1, 4 here, 1, 2, 3, 4. Even if you follow here 1, 2, 3, 4. So the correct numbering here is benzene 1,4-diol, otherwise known as hydroquinone.
Two groups of aromatic compounds. We have the arenes,
Arynes.
and the aryl group. Arenes, arynes, and aryl groups. The pronunciation may not distinguish them, but look at the spelling carefully. Arenes are aromatic hydrocarbons that include benzene and other derivatives of benzene containing only carbon and hydrogen only. They include benzene, toluene, styrene, xylenes. Xylenes are actually the dimethylbenzene, benzoyl propane. Note, not all aromatic compounds are arenes, but all arenes are aromatic compounds. See the illustration here. Arenes are actually hydrocarbons, but they are aromatic hydrocarbons. That is when they contain only hydrogen and carbon. We call them the arenes. We'll take a look at what we are going to give you here now. So if there is any other element present in the benzene ring apart from hydrogen and carbon, it is no longer an arene, but it is still an organic compound belonging to the aromatics. So watch our illustration below. As we told you earlier, of course. Over here we are seeing a methylbenzene. Throughout we have here only hydrogen and carbon. Hydrogen and carbon. That's C7H7. That's for toluene. But here we have phenol. Phenol, when OH is substituting one of the hydrogen, because of the oxygen there, this is no longer an arene, but it's still an aromatic compound. So distinguish arenes from other aromatic compounds. Then the second group, called the arynes. The arynes are actually compounds formed from arenes. They are special arenes. They are formed from arenes by removing two adjacent hydrogen atoms from the benzene ring to convert one of the double bonds to triple bond. Actually, not anytime you remove two hydrogen atoms from a benzene ring, you call it arenes. No, it must be adjacent such that one of the double bonds in the benzene ring is converted to triple bond. All arenes are short-lived. They are very, very reactive. They disrupt so quick and therefore occur as intermediates in number of reactions. So it is still showing that no stable aromatic compound has carbon atoms less than 6. So when you tend to bring such, they disrupt with short time. A common example of an arene is the benzyl.
as we are showing you the structure there. You see the benzyl there. So what we have at the end is C6H4. Don't confuse benzene with phenylene. Phenylene is just a substituent group, but benzene is a compound, though it is transient, it's short-lived. Phenylene, you may not remove the adjacent hydrogen. Phenylene is just a substituent group when you have removed any two hydrogen atoms from the benzene ring. Phenylene don't have triple bonds. It is just a bivalent group remaining after two hydrogen atoms in a benzene ring has been substituted. So refer to our next tutorial that substituted compounds of benzene. You see the difference here. Next group is actually the aryl group. The aryl groups, or the aryl group, these are substituent groups obtained by removing a hydrogen atom from an aromatic compound. So if you remove a hydrogen atom from any aromatic compound, you have a group called aryl. It is similar to that of alkyl, we all know in the aliphatic compound. Alkyls, represented by the letter R, are actually formed by removing one hydrogen atom from an alkane. Here, an aryl group is formed by removing one hydrogen atom from the benzene ring, leaving a substituent group with the formula C6H5. Other derivatives of benzene formed by substituting one hydrogen atom in the benzene ring with their old names and IUPAC names. So they have old names because organic compounds were long discovered before they were studied, their structures, or before their names were formalized. So some of them still are known by this.
When one of the hydrogen atoms in the benzene ring is substituted by an OH group, that's hydroxyl group, we call it benzenol, commonly called phenol. This is actually an alcohol. Then when one of the hydrogen atoms is substituted by a nitro group, that's amino group, we call it benzene amine, commonly called aniline. Then when one of them is substituted by a methoxy group, we call it methoxybenzene. Methoxybenzene is commonly called anisole. Then the most common one we know, toluene, is formed when one of the hydrogen atoms is substituted by a methyl group called methylbenzene or toluene, which is a known solvent. Then when one of the hydrogen atoms is substituted by an ethene, we call it phenylethene, commonly called styrene or vinyl benzene. Vinyl benzene. Then a situation whereby the carboxyl group, the COOH, substitute one of the hydrogen atoms, we call it benzoic acid. You put it to show the resonance structure. Okay. Then when one of the hydrogen atoms is substituted by NO2, we call it nitrobenzene. Then when it's substituted by one is substituted by CHO, which is the functional group for the aldehydes, we call it benzaldehyde. Benzaldehyde, or you can call it benzene carbamide. Then important substituent groups in naming aromatic compounds. This will help us a lot as we enter into the main topic to name aromatic compounds. The common one we should know first is the phenyl. Phenyl should not be confused with phenol. Phenol is an alcohol. Phenyl is a substituent group.
Phenyl is actually when a benzene ring is attached directly to a parent chain, like an alkyl group. We call it phenyl. Phenyl. Benzene ring, when it occurs as a substituent group, we call it phenyl with the molecular formula of C6H5 because one of the hydrogen now is replaced, and that is the means at which it is attached to the parent chain. So we call it phenyl. So if you see this, you name the alkyl, then call this phenyl as a substituent group. Then another one is the benzyl group. Benzyl group. The benzyl group and phenyl should not be confused. The difference here is that the benzene ring attaches to CH2 before getting to the parent chain or the R or car. This R can be a parent chain form of an aliphatic compound. Benzyl and phenyl should not be confused. Benzyl have CH2 coming off the benzene ring before getting attached to the parent chain. In other words, this should be C6H5 for phenyl, while this should now be C1, 2, 3, 4, 5, 6, and 7. C7H, this should be 2 plus 5 that are here, so C7H7 for the benzyl group, while here should be the phenyl group, that's 2 3, 4, 5, 6, 7 for phenyl. Then to apply what we just said now, watch over here. Take a look at this compound here. This substituent group is benzene attached direct to the main parent chain, so this should be called phenyl. While here now, before the benzyl attaches to the principal function, the main carbon skeleton, you have the CH2 coming off the benzene ring before the parent chain. So this here is called Benzyl Group. So in naming, we have 4 carbons, 1, 2, 3, 4, and hence boot. Then in numbering, you see 1, 2. At carbon number 2, you have a substituent group, which is called phenyl. So you call this 2-phenyl butane. While this, the same thing butane, but numbering there is carbon number 2. But what left at carbon number 2 is benzyl, no longer phenyl. So you can call this now 2-benzyl butane, while this is 2-phenyl butane. Another illustration to show the benzyl group. Benzyl group, you have the CO substituting one of the hydrogen atoms, and this is important in benzylation reaction. Another good example that we may be using is a bivalent substituent group, which is called phenylene. Phenylene is just the substituent group that remains by removing 2 hydrogen from the benzene ring. Remember phenyl, you remove only 1 hydrogen from the benzene ring. Then here you attach it to methylene group before the parent chain. So phenylene is having the molecular formula of C6H4. Watch this. The 2 hydrogens has been replaced by amino group. So we are now left with only 4H, 1, 2, 3, 4, and the 6 carbons. So if you remove this 2 amino groups, the other part of benzene remaining is called phenylene. So if you are asked to name this compound, you now call it phenylene diamine because there are 2 amino groups. Phenylene diamine is a substituted compound of benzene. Now, further examples, see this compound here. Here is carbon 1, 2, 3, 4, 5, 6, 7, and 8. So there are 8 carbon atoms in the parent chain or in the root. Hence, the root is now oct because of that 8. Then you look for the functional group, the principal functional group, which is actually OH. Now you number the carbon atoms. Among these 8 carbons, which one will be number 1? You number from the end closer to the functional group, which is this OH. So this is carbon 1, 2, 3. So at carbon number 3, there is OH. 4, 5, 6, 7. At carbon number 7, there is a phenyl. Remember, benzene ring branching off the parent chain is called phenyl. Then at carbon number 4, there is a methyl group. We have to name methyl before phenyl because of alphabetical order. Therefore, the name of this is 4-methyl because it occurred at carbon number 4, 7-phenyl octane 3-ol. Or you can call it 4-methyl 7-phenyl 3-octanol. That is it for this way it is explained. Methyl, which occurs at carbon 4, phenyl group at carbon 7. Now, watch this other example. It shouldn't confuse you also. This is phenyl group, and the same number you have 1, 2, 3. The parent chain is propane, but because there is OH, you substitute the E with O. It becomes now propanol. But the propanol occurs at carbon number 2, and then the same carbon number 2 bears phenyl. So the name should now be 2-phenyl propan 2-ol or 2-phenyl 2-propanol. Simple as that. Don't get confused. This structure here is similar to writing it this way. Then you have the OH here, saturate everywhere here with hydrogen, so that it remains the same thing. More complicated structure, but when we follow it with carefulness, we won't make mistake. Watching the drawing shows that there are 2 phenyl groups coming out from the main chain. Then the functional group there are 2 functional groups actually, the OH there and the COOH. But here, COOH is the principal functional group. Therefore, OH will now serve as a substituent group. So we have OH as a substituent group, and now we have also 2-phenyl as substituent group. The structure here is the same. In case if the other one is confusing you, watch it now. We have 2 carbons there. Therefore, in our numbering, the carbon bearing the COOH will actually be carbon number 1. We are showing you the main functional group there. So our parent chain is et because it contains 2 carbon, and the functional group there is COOH. Then we have ethanoic acid first. So at carbon number 2, you notice there is OH there, and the same carbon number 2 there is phenyl group, which gives us 2,2-diphenyl and then 2-hydroxy. In alphabetical order, there should be hydroxy before phenyl. Therefore, the name is 2-hydroxyl 2,2-diphenyl ethanoic acid, commonly called benzylic acid. these are the same thing. The two compounds are the same. Okay, be careful to know the difference between alkanoic acid as a group and alkanals and alkanones. Watch carefully. When you have double bond attached to one oxygen and the single bond attached to OH from the parent chain, that should be carboxylic acid, that's alkanoic acid. But in the other hand, watch this one. There is no OH, there is only H. This should be alkanal. Therefore, the main functional group is HCO. So over there, watch very well. What we have is COOH. That's why we call the initial one alkanoic acid, that's ethanoic acid. Then watch when it is alkanone. There will only be double bond to O, and there is no hydrogen at all. So watch the tray. Okay, let's take a look at another compound here. This may appear to be complicated, but still simple. Okay, watch well. There are actually the CO here, C double bond O, and our parent chain contains 2 carbons. The substituent groups are actually phenyl. There are 2 phenyl groups in this compound. Our root is et. Because of the C double bond O, we now call it ethanone. You replace the E with ONE to give you ethanone. Then at carbon number 1 and 2, whichever direction you move, you still get 1 and 2. So we have at least 1,2-diphenyl ethane 1,2-dione.
Consider this compound. These two are the same thing. Watch well. There are 2 hexagons, but there is no ring here, which means this is not a benzene ring. This one shows benzene. So these are parent chain, which is an aliphatic compound, cyclic aliphatic. Therefore, we number from the side that gives us the lowest possible number to the functional group. Moving from this direction, 1, 2, 3, you get the functional group at carbon 1 and number 3. For someone that numbered here 1, 2, 3, 4, 5, we have 1, 5. So the correct numbering is as shown here, 1, 2, 3. So we have, because of this, we now have cyclohexane 1,3-dione, because this is alkanone as a functional group. Then from this number, we say at carbon number 5, there is a branch. And this branch is not phenyl, rather it's benzyl, because there is CH2 in between the parent chain and the benzene ring. That makes this group now a benzene group. So we call this 5-benzyl cyclohexane 1,3-dione, or 5-benzyl 1,3-cyclohexane-dione. That's it. The same thing is applicable here. These 2 compounds are the same. If you number from this direction, let's take 1, 2, 3, 4, 5. It will still give you 1, 3. If you start here, 1, 2, 3, 4, 5. So this will give you 1 and 5, which is not correct. You take the direction that gave you 1, 2, 3. 1,3-dione is lower than 1, 5. If you take this direction, you get 1, 2, 3, 4, 5. 1, 5, which is wrong. So if you follow this pattern, you still see the Benzyl group at carbon number 5. So that's it. This is another example. Be careful, this and this are not exactly the same in numbering. The position of the Benzyl group is not the same thing with the position of the Benzyl group here. Watch this. 1, 2, 3, 4. You get 1,3-dione. At carbon number 4, we have benzyl. But here at carbon number 5, we have benzyl. Let's check who numbered this way. 1, 2, 3, 4, 5. This numbering is wrong, though it's giving 1, 2, 3, 4. It is giving the benzyl group the same number 4. But because of the functional group, this is the correct direction. 1, 2, 3, 4. So that we have 1,3-dione. So this and this are nearly the same, only that the position of the benzyl group is not the same. So here, the name of this is 4-benzyl cyclohexane 1,3-dione, or 4-benzyl 1,3-cyclohexane-dione. The only difference is the position of the benzyl group. This is at carbon number 4, but here it is at carbon number 5. So the name of these two are the same nearly, only that the substituent group here, benzyl, is at carbon number 4. So this is 4-benzyl 1,3-cyclohexane-dione. Here is another example. Let's follow the steps carefully. We count the main chain. These and these are the same. In case if you don't understand this structure, you follow up here. each of these edges means one carbon. This is 1, 2, 3, 4, 5, which is the same thing as 1, 2, 3, 4, 5. Please, here you don't count from here because this carbon belongs to the benzene ring. Therefore, the parent chain in this case is pent. So we have the name pent. Because there is single bond throughout, we have pentane. Then we number to give us to identify the position of the substituent group. Our substituent groups is only, there are two different types, the methyl and the phenyl. We have two phenyl groups and one methyl. Remember, alphabetical order, there should be methyl before phenyl, M before P. Therefore, if you number in this direction, 1, 2, 3, you get it at number 3, 3 methyl. If you hear 1, 2, 3, you still get 3 methyl. But let's consider the other one. If you number here, you have 1, 2, 3, 4, 5. So you have 3, 5 diphenyl. But here we give you 1, 2, 3, giving it 1, 3 diphenyl. So this direction is correct numbering. So here should be 1, 2, 3, 4, 5. So by so doing, we have 3 methyl, 1, 3 diphenyl, 1, 3 diphenyl pentane. 3 methyl, 1, 3 diphenyl pentane. That's the name of this compound. In this compound, watch closely, we can't count here as part of our parent chain because this carbon belongs to the benzene ring. So we have only one carbon in the main chain. This time around, 1 is met and there is no double bond at all. So what we have as our root is actually maintained. This carbon number 1 bears phenyl, 2 phenyl. So actually what it should be now is 1, 1 diphenyl, but because 1, 1 there is no other alternative, we can commonly call this just diphenyl methane. Simple. Diphenyl methane, because here is a phenyl, here is a phenyl attached to one carbon in the center. That's why we call it 1, 1 diphenyl methane, because there is no other way. That's why we can remove the 1, 1 and just call it diphenyl methane. Here is another example. These are the same thing, just showing the different ways you can represent them. Remember, if this triple bond is very close, if it is distant, it means there is another carbon here. So we have 1, 2, 3, 4, 5, 6, which is also the same thing here. So in each direction we have 1, 2, 3, 4, 5, 6, and hence the root is hex. Then the functional group is triple bond, which is ine, and the triple bond dropped off 3 carbon on each side. So we take the one, they are all equal. Normally we should take lower one between 1, 2, 3, 1, 2, 3, but here they are all equal. So we say 3 hexine or hex 3 ine, hex 3 ine. Then the substituent group is at carbon number 2. You should start from this direction because this is the direction I'll give you lower number. If you start here, it becomes 1, 2, 3, 4, 5. That's 5 phenyl. But if you start here 1, 2, it becomes 2 phenyl. Since we get the triple bond in between, equal distance in the middle, so you take the direction that gives this lower number. Assuming this our triple bond is here, that forces us to number here 1, 2, 3, 4, 5. Then we'll take 5 phenyl. But as far as this is concerned, this should be 2 phenyl. So the name of this compound is 2 phenyl hex 3 ine. 2 phenyl hex 3 ine, 2 phenyl or 2 phenyl 3 hexine. Okay, consider this last example. Remember, you not start at this end unless there is nothing again attached to it. But with this, it shows that this is the carbon here is not part of the main chain, it's part of branch, just like the carbon here belongs to the benzene ring. So we have 1, 2, 3. The name of this compound is 2-amino 3-methoxy 1-phenyl-propan 1-ol, or 2-amino 3-methoxy 1-phenyl 1-propanol. Watch this, the parent chain is 1, 2, 3, 3 carbons, and the OH is the principal functional group, and hence that determines our numbering. The carbon bearing the OH becomes number 1, followed by this bearing the amino group number 2, followed by this bearing the methoxy group number 3, and hence 2-amino 3-methoxy, and finally 1-phenyl, because the phenyl group is also attached to carbon number 1.